Okay, having learned about electric forces, this lesson is about electric fields. So the idea here is that all charges have fields that surround them and interact with other charges. So there's electric fields surrounding charges. In other words, charges influence the area or field around them. And we call this phenomenon the electric field. And it's defined as the force that we do experience by a unit positive charge. So what I mean by that is we've previously learned that, say you have like a 1 microcoulomb charge here, some distance away you maybe have a 2 microcoulomb charge, and we know that there's a force acting between them, and that's governed by Coulomb's law, Q1, Q2, R squared. So we know there's a force acting between two things. So then let's suppose we have some charge here, Q, and then some distance away from the Q, we have another charge, and it's 1 coulombs, and it's some distance R away. We know that the force here is KQ times 1 divided by R squared, and that's also the definition of electric field. So electric fields are vectors, they have direction. So this would be KQ divided by R squared. The directions that we give electric field is we work under the idea that what would a positive charge do within the field of another charge. So we call it a positive test charge. So if we have a charge here, say 3 microcoulombs, and I want to know what the electric field is at that point there, well, we say, well, if that point was a positive charge, what would it do? So if this is positive, this would want to be repelled. So the direction of the electric field in this case would be to the right. If we put a positive charge here, we want to move there, so the electric field direction is that way. If we put a positive charge there, it will want to repel in this direction. That's the direction of the electric field. If we had a negative charge, let's suppose we had a negative 2 microcoulomb charge, and we want to know the direction of the electric field there. Well, if we put a positive charge right at that X, it's going to want to be attracted to the negative. So that would be the direction of the electric field there. If we put a positive charge there, go this way, charge there. So electric fields are pointing the direction a positive charge would point. Actually, I have a simulation for this. This simulation shows electric field direction. If I put a positive charge there, and you can see no matter where I move the charge, the direction of the electric field is always pointing away. Negative, it's always pointing towards it. And if I put more negatives there, the electric field gets bigger. Okay, so back to this. So the equation is KQ over R squared. It's not energy. I guess if we put the vector sign on top of it, that should remind us that's not energy, because energies are not vectors. So KQ over R squared. They have both size and direction. Okay, so there's a lot of similarities between electric fields and gravitational fields. So gravitational fields give gravitational forces, and electric fields give electric forces. We have something called the gravitational field strength. G was equal to G m over R squared, and electric fields, and this always had direction too, actually. Electric fields, it's K So instead of an M, it's a Q and R squared. The big difference between electric fields and gravitational fields is G is always attractive, but electric field can attract or repel. So that's interesting. Do a couple of problems here. Find electric field strength 0.45 meters to the right of a 2.3 microcoulomb charge. So we have R is 0.450 meters. Q, little q would be a Q, I don't think it really matters. 2.3 times 10 to the negative 6 coulombs. Electric field strength. And actually, I'll do a little drawing here. Here's my charge. It's a positive charge. And we want to know the electric field strength there. So if I have a positive charge here and I'm looking at a place there, that direction's going to, if I put a positive charge on that X there, it's going to want to move to the right. So that's the direction of the electric field. So we got K, Q over R squared. So K, 2.3 times 10 to the negative 6, 0.45 squared. Don't forget the square. Let's put that in the calculator. Let's go 9 to the power 9, 2.3 e negative 6, and 0.45, and square that. We got 102,000. So we'll go, maybe we'll call it, oops. 1.02 times 10 to the 5th. What are the units? Well, we have a coulomb up top. Actually, yeah, what should we call these units? I was going to work them out from these basic things, but I don't really talk about the units of K too much. It's a electric. Actually, this is another thing that's going to be pretty important. There's a it's just understanding the relationship between electric field and force. So as an equation, you should also write this down. So it's electric force per coulomb. The units for force are Newton, and charge is a coulomb. So those are the units for electric field. You're ready. Let's do a couple more. We have a charge and field strength. What's the distance? So rearranging this equation, we'll get R squared equals KQ over E, or R is equal to K times 0.5 microcoulombs divided by 3.1 times 10 to the 4, square root that. So let's put that in the calculator. So we get 99.5 e to the negative 6. And then divide by 3.1 times 10 to the power 4. And then I'll take the square root. I got 0.38 meters. What would be the field strength if the distance is 3 times larger? Well, this is another inverse square relationship. So if you were to graph R versus E, you would get something like this. So if R doubles, E goes down by 4. If R triples, E goes down by 9, and likewise. So if the field gets 3 times larger, this thing's going to get smaller by 3 times. So we divide that by 3. Or 9, sorry. If the distance gets 3 times larger, the field strength will go down by 9. So I'm going to go 3.1 times 10 to the power 4 divided by 9. So that's 3.4. What was times 10 to the 3 newtons per coulomb. Alrighty. Looking at direction of fields a little bit more. Since electric fields are vectors, we need to learn how to illustrate it. I've already talked about this. When drawing field lines, we say the direction of the electric field is the direction the positive charge would go if it's placed at that point. I don't know why I have that there. So we should also draw our electric fields as the bigger they are, they have bigger arrows. So if we're really close to a charge, the field strength is quite big. But if we're further away, the charge would be smaller, or the arrow would be smaller. And if we're really, really, really far away, it'd be like just really small. When two charges interact, we get what's called a dipole. So these from this charge, the field is going to the right. From this charge, it's going to the left. And what we get is something that looks like this, because field lines never cross. So that's an important thing to know. You're going to see in all my drawings here that I never show field lines crossing. These ones will attract, so this will be like this. Just go straight across. Oops. Yeah, these ones go like the other way. Those go away. Something like this. And I actually meant this to be two negatives. And it's similar to the other one, like this. So again, the field lines never cross. That's a negative. Okay, that's what field lines will look like. Okay, another word problem. Test charge experiences a force towards the south. Find the electric field strength at this point. So we have a test charge here, and it's a negative 0.5 microcoulomb test charge. And it's experienced a force downwards like this. We know that is equal to 5.2 times 10 to the negative 4 newtons. And the question is, well, what's the field strength that's causing that sort of force? So the definition of electric field is force per unit charge. We don't yet know the force per unit charge. In this case, we know the force for a negative 0.5 microcoulomb charge. So to get the unit charge, we have to divide by that charge. To get the electric field strength, we need to take that force and divide by the charge. So electric field is the force divided by the charge. So that tells us this is 5.2 times 10 to the negative 4 newtons divided by negative 0.5. Actually, the negative sign doesn't really need to be here because it's a vector. So we'll talk about the direction in just a second. This is 0.5 times 10 to the negative 6 coulombs. So the electric field vector is 5.2 e to the negative 4 divided by 0.5 e to the negative 6. I get 1040 newtons per coulomb. And then the question is, well, what direction is that electric field? So if a negative charge is moving downwards, what would a positive charge do? A positive charge would point the other direction. So this would be north. Again, the direction of an electric field is always the direction that a positive test charge would be, would have. Okay, another example. Find electric field strength direction. So electric field are vectors, so you could have different fields adding up. So we can, but we don't add them up as like arithmetic sums. We add them up as vectors. So we have to consider the direction. So maybe I'll call, I'm going to call this E1 and this will be E2. And we're looking for that point right there. So E1 is K 1 microcoulombs divided by 1 squared. So K is 9 times 10 to the power 9 times 1 to the power of negative 6. So this is going to be divided by 1. So the bottom doesn't do anything there. So this is 9 times 10 to the power of 3. And that will be to the right. At this point, it's going to be repelled from the positive. Okay, let's look at E2 here. Ooh. So, okay, same size charge. This time it's a lot further away. This is 1 meter and that's 4 meters. This distance here, it's going to be 3 meters. So R is 3 squared. So this is 9 times 10 to the power 3 divided by 9. So we get 1 times 10 to the power 3 newtons per coulomb. And this one, at this point, the field caused from that charge will be to the left. So we have one big field there, smaller field there, and then that will be the total field. So it's the difference between the two and to the right. So E total is, well, 9 minus 1. 9 minus 1 times 10 to the power 3. So E total is 8,000 newtons per coulomb to the right. Okay. Couple more questions. Find the electric field midway between these two charges. That's A, and then B is where so I'm going to do the A first here, obviously. R is equal to 2.5 meters. That's for both cases. So we'll do this. I'll call this one E3. I'll call this one E2, just because that's the size of the charge. So E3 is K 3 microcoulombs divided by 2.5 squared. So it's 9 E9, 3 E negative 6, 2.5 squared, 4320. And that would go to the right. E2 is K 2 microcoulombs, 2.5 squared. So that'll be 2/3 of that. We'll multiply that by 2, divide by 3, so that's 280. That one will be to the left. So this is similar to the previous question. So E total is the difference between those two. E3 minus E2. So that's going to be 1440 to the right. I think you could have just done it proportionally anyways. If it's right in the middle, and or maybe, I don't know. You probably could have done it proportionally. Anyways, that's the answer. Next question is, where's the electric field 0? So this is kind of interesting question. This is like a Math 11 rational expression type question. Somewhere along this line, this force will be 0. The field would be 0. Because the field is equal and opposite from the two charges, at some point they cancel each other's out. So I'm saying there's some point here, some distance x away from here, some 2 microcoulomb charge, where the force is, or the field is 0. So, and the way it adds up is there's at some point the electric field total 3 minus 2 is 0. In other words, it's where these two are equal and opposite at some distance. So we have E3 is K3 over 5 minus X. We can call it microcoulomb. That's E3. And E2 is K 2 microcoulombs X. Actually, this is all squared. We can drop the microcoulomb part. It's at this point we're working with the proportion, so the microcoulomb part doesn't matter. Same with the K. It'll cancel out from both sides. So we just have a rational expression. So I'm going to multiply both sides by x squared. So I get 3x squared. And I'll multiply both sides by 5 minus x all squared. That's one way to solve rational equations, is to multiply everything by the common denominator. So this side I get 3x squared, and this side I get 2 times 5 minus x all squared. So it's 3x squared minus, I guess I'll expand it to, 25 minus 10x plus x squared. So 3x squared is equal to 50 minus 20x plus 2x squared. And I'll subtract 3x from both sides, so I get 0 is equal to 2x squared minus 23x plus 50. So now we just have to solve that quadratic. Is that 100? So it's 100 and we've got 50 times 2. Oh, 20 times 4. I think we have to use quadratic formula for this. Actually, I think there's an easier way to do this. I'm going to take the square root of both sides. So I get root 3x equals root 2 5 minus x. So I get root 3x. If I distribute the root 2 and I move things over here, I get plus root 2x minus 5 root 2 equals 0. Actually, I'll just keep it on that side. So I get x, I factor out the x, and I get root 3 plus root 2 equals 5 root 2. So x equals 5 root 2 over root 3 plus root 2. Calculate that and just double check. So we get root 2 times by 5, and then in the denominator I have root 3, and I have root 2. Add them, divide, and get 2.247. All right, so let's check it out. Electric field caused by the 2 microcoulomb charge, 2.247 away. All right, so I go, I'm going to just look at this proportion again here. I don't need to calculate the times 10 to the negative 6s and the 9s because they cancel out. So I'm going to go 2, and I'll take that distance, I square it, and divide. So that's 1 is, this E is 0.396. And the other one is 3, divide that by, nope, first of all I have to subtract 5 from that distance. Oops. So square that, divide that, you get the same number. So that checks out. All right, that's kind of a hard one because of the math. The last thing to do is I'd like you to sketch what direction the field lines will be at each one of these points if you have a negative charge here and a positive charge here. And to do that, you can use this PhET simulation to help you draw it. So you can set this scenario up to help make sure you're drawing your electric field lines correct. Okay, good luck.